All right. So for this second part, we're just gonna briefly talk about some other ways in which we can measure strain. So as I said, for the geometric nonlinearities, there's the nonlinear displacements, and so the first two examples were about just nonlinear displacements, even though we had linear functions of strain and linear functions for the stress actually as well. But the first thing that we're gonna do that is really more relevant to what we're gonna do is find definitions of nonlinear strain. And there are several different alternatives, and these are going to make more sense later on. So again, if you go back to the simple linear 1D approximation, we had that the strain linear was just the delta L, so basically L minus L over L, right? That was if you have like some bar and you stretch it, right? So it's originally length L and ends up being of length lowercase l, then the linear strain would just be the difference between the initial length, right? So that would be one approximation of the strain. But in reality, if you want to rather integrate this, so integrate this along the bar. So if you integrate this for very small pieces of of the bar, and you integrate every little bit of this strain, then you end up with this logarithmic strain. So that's how you end up with this guy. It's basically just the integral of this guy over some bar. And then the ones that are going to make more sense later on, but just take them for granted right now, are this Green strain or Almansi strain. And these are just basically the difference of the square of the lengths divided by the square of the length. And it's just, if it's divided by the reference length or divided by the deformed length, you're going to get something slightly different. And yeah, again, we'll talk more about this, but these are just take it for granted right now that these are better definitions of the strain. So these and these they will come up naturally later on. But these are just better. And they are clearly nonlinear, right? So whereas this one is a linear function of L, now we have L squared, for example, here. So here, in the Green case, even though the denominator is a constant and L squared is a constant because the initial length is a constant, we have some nonlinear, just a quadratic, but that's still nonlinear. In the case of the Almansi, you have both nonlinear term in the numerator, and you also have this nonlinear term in the denominator. And then clearly logarithm is a nonlinear function. So if you have logarithm of L, then that's obviously some nonlinear function of the strain. So again, we went from what you would typically think of in a very simple setting, what would be the linear approximation of the strain, just the change in length over the original length, to at least 3 definitions of strain that involve some nonlinear function of this deformed length L. And to show you how this would look in an example, I took this from the book by Bonnet and Wood on nonlinear continuum mechanics. So again, you have this just simple bar. So you have this is the original location of the bar, which has some undeformed length L, some cross-sectional area A, some volume V. And then you apply some force. And then due to that force, the bar moves up, and then it gets stretched. So now you have some deformed length little l, some deformed area little a, so assuming compressible. Which means little b equals big B, so the volume stays the same, right? And then how do we parameterize this? We can parameterize this with this coordinate x. So this is a one-dimensional problem, so there's just a single coordinate. So let's treat this as the independent variable. And we can use, to calculate the stress in the bar, we can use one of our, instead of the usual just sigma, or the stress, equals Young's modulus times some nonlinear function of the strain, we can use one of these definitions of the strain that we just introduced. So now we have the stress is a function of this nonlinear strain. So it's a linear function of the strain, but because the strain is nonlinear, it's going to be a nonlinear function of the variable x. So if you do the balance, the force balance, we're going to get t minus f equals 0, where t is basically the force from the bar. So that would be the stress times the area, so that would be the force, and then times the sine of the angle theta, right? So that we get only the vertical component of the force. So that minus f equals 0, and then you can substitute, instead of sine theta, we want to put it in terms of x over L. And then if you want to substitute the stress, you can use either one of these. So let's say we write it in terms of the logarithmic one. So then we have E times A times the logarithm of L over L times x over L minus f equals 0. Because we have incompressibility, so because incompressible, then V equals V, right? So AL equals AL equals V. So we can rewrite it as E times V times x over L squared logarithm of L over L minus f equals 0. So that would be the equation. Now if we want to put everything in terms of a single variable, so let me just copy this. So that's it with L squared equals D squared plus X squared. So if you plug this here, then you're gonna end up with a single equation in terms of X. Right, I mean, I could write it out. So EVX, and then right here L squared, which is just D squared plus X squared, logarithm of L, which is the square root of D squared plus X squared over L minus f equals 0. So this is the equation that I need to solve with the logarithm strain. So clearly nonlinear in x. So if I give you some force F and I ask you to calculate the displacement x, then you would have to solve this nonlinear equation. And you can get a similar expression, but in terms of the Green Lagrange strain. The only thing that would change is this part right here, right? So instead of that logarithmic strain, you will get the other, for example, the green strain. And yeah, so you have to solve this. Again, this is a nonlinear function. And what happens if you solve? Then you get something that looks like this, where this is the displacement x, and this is the corresponding force. And then we're gonna talk a little bit more about this, but you can see that this changes. So as you are moving, you are compressing the bar, so it gets it's under compression, and then as you pass so this will be, the bar gets compressed, right? And then at some point they still compress, so between here and here, that's sort of like a compression part. And then at some point it's gonna be under tension. So here, let's say that here on, it's gonna be under tension. So that's why you cross this 0. So now from this point on, it's under tension. And the interesting thing here is that If you look at this in terms of x, for example, there's a single value of the force. But if you look at it the other way, so if you are given a force and you want to calculate a displacement x, now there are points of the force for which you have multiple solutions. So for example, if you are, if you tell me some value of force down here, then there's different possibilities for the displacement x that give you the same force. So that's going to be something that is kind of tricky, and we'll talk about that in the future. So these are there's some snap through instabilities that happen here where you have this force that increases, then decreases, then increases again. So we'll talk more about that. So that's just something to keep in mind. Yeah, but that's it. But if in this case, the way I evaluated this, I just put in x, calculated the force, then there's no problem, right? So if you are given the displacement, easy. Typically, what's the problem that you're solving is actually you are given the force and you are asked to calculate the deformation. So in that case, as I said, for this particular scenario, you have multiple solutions for a given force. So how do you solve for that? We'll talk more about that. But you can see that in either case, the function is clearly nonlinear, right? And then there's not that much difference between the green and the logarithm strains, up to a certain value of the displacement x. Obviously, as you go higher and higher, then there is some difference, but in the small deformation, it's okay. They are very similar to each other. All right, so that is one of the first concepts that I wanted to do for nonlinear, more related to what we're going to talk about in this course, which is nonlinear strains. And the other one is nonlinear stresses. So hyperelasticity, meaning some nonlinear stress. So in the previous one, I basically went from strain is no longer just the change in length over the original length. Now here, I don't want this, right? So I don't want this definition of the stress. I want something a little bit more general. And then I'm not going to go over the details of this. This is reserved for some later lecture. But the framework that we're going to use is called hyperelasticity. And that requires that you define some strain energy function. So just take this for granted. This is called an Hookean material with parameters mu and lambda, which are called the Lamé parameters. And then it depends on these variables. So the variables that go into the strain energy are this I1 and this J. So the parameters are, so these are sort of like deformation. So I1 and J, it's written right here, but I1 and J are related to the deformation. Mu and lambda are material parameters. And you can evaluate the strain energy. If it helps, you can think of this as, for example, for a spring, you can define the energy as 1/2 k delta x squared. So this is sort of a generalization of that idea of finding some energy for some spring. So think of the material as spring in 3D. I don't know if that helps. Anyways, so given that strain energy, you can get the stress. So I'm gonna skip through how did I get this, but the stress is, again, related to the deformation. Now the stress is a matrix, so in this case, well, it's a tensor, but let's simplify that and let's call it a matrix, where the mu and the lambda are still the parameters that I introduced before. The J is still related to the deformation, and I is the identity, and B is this guy. So this B is going to appear a lot later. For now, just believe me that this B is F times F transpose, where F is a local deformation matrix. So F is some 3x3 matrix that describes the deformation. Again, don't try to think too much ahead of this. Just believe me. So now I have a definition of the stress that is nonlinear on the deformation. So you can see, for example, that we have this term logarithm of j. So that's clearly nonlinear function of the deformation. So j is part of the deformation. J is the determinant of that f. And this function b is going to be also nonlinear because it's f times f transpose. So if f describes the deformation, this b, which is f times f transpose, is going to have like quadratic terms. And so this will be also nonlinear. So the b will have some quadratic terms, so that's going to be nonlinear. And then we also have this logarithm of the Jacobian, which is also nonlinear. So now you can see that we went from having the stress being a linear function of the strain, to the stress being some nonlinear function of the deformation. And again, you don't have to understand the details, but just that there is such a thing as this nonlinear definition of the stress. And so how can this be useful? For example, let's say that I want to do a uniaxial test of a compressible Nehookian material. And I have a bar or cube that is originally length L, and I want to deform into something that is length lambda 1 times L. Don't confuse this lambda 1 with the Lamé parameter. I may be a little bit confusing, but this lambda 1 relates to the deformation along this axis. So the f for this uniaxial case would be lambda 1 in the first direction, which let's call that x. And then lambda 2 and lambda 3 in the other two directions. So you can see that this F matrix sort of tells you how the different axes deform. And we're going to come back to that later on. But for now, I think that will be enough to think about. So lambda 1 is basically the stretch in the x-axis, lambda 2 is the stretch in the y-axis, lambda 3 is the stretch in the z-axis. And so if you just want to evaluate the stress in this case, you see that the stress needs this B matrix and also needs the Jacobian, right? So let's evaluate the B matrix. So the B matrix, which is just F times F transpose, is going to be lambda 1 square, lambda 2 square, and lambda 3 square, and then zeros in the other entries. So this is what I was saying, that this B matrix is nonlinear because it will have these quadratic terms for the deformation, so quadratic stretches. And then the Jacobian is just the determinant of F. So in this case, lambda 1 times lambda 2 times lambda 3. And then simplify, because in this case, you can assume that there's no constraints in either the y-axis or the z-axis, so you can say lambda 2 equals lambda 3. Let's just call it lambda 2. So B, we're gonna simplify this a little bit. So lambda 1 is what we control, so that one stays the same. But there's no point in keeping lambda 2 and lambda 3 because they are the same. So because the problem is transversely symmetric, I guess. So we're applying the lambda 1, there's no difference really in the y and z axis, so they should deform equally as long as the material is isotropic. All right, so these are the two definitions, the two things that we need to define the stress. So if you go back here, the stress, basically all I need is B, J, and the material parameters, mu and lambda. So I could have, so now my stress is going to be mu over lambda 1, lambda 2 square, times this matrix, which is lambda 1 square, lambda 2 square, lambda 2 square, minus the identity, which is just 1, 1, 1, plus lambda. Don't confuse this. This is the Lamé parameter lambda. Maybe I should somehow make it look like a parameter. I'm just going to use a different color. Mu lambda, so that it's clear that those are material parameters and not part of the deformation. Lambda 1, lambda 2 square, logarithm of the Jacobian, which is lambda 1, lambda 2 square, times the identity. So 1, 1, 1. There we go. So that's the stress, right? So it's a 3 by 3 matrix. And then, so which one are the unknowns here? So lambda 1 I control, because in this case, typically I would specify, so if you were doing this material test, you would actually control the displacement in the first direction and measure the force. So in this case, you can do, you know, given lambda 1, solve for lambda 2 and sigma 1, 1. So these are my unknowns, lambda 2 and sigma 1, 1. And then lambda 1 I know. Let's say I know lambda 1. I still get a system of equations. So if you just go, so sigma 1, 1 is mu over lambda 1, lambda 2 square times lambda 1 square minus 1 plus, let me also redo this. Over lambda 1, lambda 2 square, logarithm lambda 1, lambda 2 square. So that's one equation. And then the other equation is, you can see that here everything is 0. So for the stress, everything is 0 except the diagonal could be non-zero. And then what happens is that there's no forces applied to either of the I guess y or z planes. So because of that, then we have sigma 2, 2 equals sigma 3, 3 equals 0. So that gives us another equation, which is 0 equals, and then it's pretty much like this one. Pretty much like this one. The only thing that will change is this is going to be 2. And that's about it. So these are our two equations. So given lambda 1, you can solve first equation 2 for lambda 2, and then just plug that in equation 1 and evaluate sigma 1, 1. Clearly, if you are solving first, for example, equation 2, it's a nonlinear function of lambda 2. So even if you put in lambda 1, then you have, you know, logarithm involving lambda 2, you have this lambda 2 square. So it's again a nonlinear function. Solve for lambda 2, plug back into equation 1 to get the stress in the first direction. So I've done that. So as you apply the stretch, so this will be the lambda 1. You can solve for lambda 2. You can solve for the Jacobian, just to show that this is compressible. Jacobian is related to the volume change. And you can solve for the stress in the first component. And again, there's Python code for this, but that's a different video. All right, so this is the end of this part of the lecture. And just to recap super quick, there's two things that I wanted to show, which were, the first one, that there's nonlinear definitions of the strain, and this will be clearer later on. And the second one is that there's nonlinear definitions of the stress. In particular, we're going to be dealing a lot with hyperelasticity, so I just wanted to give you an example of that. And that's it, and just computing with those. All right, so I'll see